Welcome to a new lesson. In the previous lesson, we studied about HDFS blocks. In this lesson, we'll deep dive into HDFS architecture. HDFS works on master-slave architecture. Name node is the master node and data nodes are the worker nodes. That means name node would be responsible for all the management of the storage space on the data nodes, and data nodes would do the actual groundwork of storing the data blocks. Name node performs the function of keeping a track of the complete file system by managing two things. First, namespace image, and second, edit logs. Namespace is the metadata about the files and directories which are stored in HDFS. It contains data about all the blocks, to which files they are associated with, and on which data nodes it resides. Edit log is nothing but the log of activities on HDFS performed by the client. Edit logs just keep on piling up and grow as the activity on HDFS keeps on happening. So out of the two, edit log is the one which keeps on growing at a faster pace. These two combined form the complete file system image, giving details of all the files and blocks on HDFS. The block information is updated by the name node as and when data nodes join the network. That means as soon as a data node boots up and connects to the network, it would send name node the information about the blocks it has, and thus name node would update the namespace image with the data. Both edit logs and namespace are maintained in the main memory of name node. This helps name node to quickly look up for the blocks as and when required. Now let us take a look at the case when the name node fails. As you can guess, the complete file system would go down and would be unavailable as complete namespace image and data block information is lost. For this reason, name node is also referred to as single point of failure (SPOF) in HDFS. That is why it is important for the name node to be resilient to hardware failures, and it is highly advisable to spend more on name node's hardware. Still, with upgraded hardware, failures can happen. To counter those situations, following resilient addition is done. The namespace image and edit logs are transferred to a highly available remote interface mount by name node from time to time. Additionally, secondary name node is also added. Do not confuse it to be like another name node. This is considered to be one of the naming blunders in Hadoop. Secondary name node doesn't function like name node. Its main and sole purpose is to combine the namespace image and edit logs so that name node's main memory doesn't fills up because of the ever-increasing edit logs. Secondary name node also creates checkpoints of the namespace image and edit logs merged together and writes it to a file. This helps name node to release the main memory occupied by the edit logs till the point of last checkpoint. And this is the only purpose of secondary name node. Secondary name node is a Java program which just combines the edit logs and the namespace and creates a checkpoint. That's it. This operation of combining the edit logs and namespace is itself complex and CPU and memory intensive. So secondary name node needs to be running on a good hardware configuration, as the job of combining the edit logs and the namespace requires good computing resources. At this point of time, I just want to remind you that the name node and secondary name nodes are nothing but Java programs that run with main classes as name node and secondary name node. So in case of failures of the name node, Hadoop administrator needs to boot up a new name node. This is the case only with the earlier releases of Hadoop. Hadoop 2.3 release and CDH4 have high availability features available in them. In those cases, this situation is a little improved. We would look into them later in the course. So in the previous releases to Hadoop 2.3 and in case of CDH3, in case of a failure of name node, administrator would have to bring up another machine as name node. Now this machine had to be of good configuration as name node system requirements are high. So in that case, most often in a small cluster, machine that ran the secondary name node is used to reconfigured as a new name node. Again, please do not confuse that it is secondary name node's function to take over as primary name node. It is not. Just that the machine which ran secondary name node is most often the best choice for the new name node in case of failure. So in case of failure, the last information from NFS mount is retrieved manually by administrator to the machine which would take over as a new name node. and the machine is then reconfigured as the name node. This process can take around 30 minutes to return to the stable state. Next, let us look at the guidelines for the name node's main memory. As the cluster size increases, the number of storage blocks that name node has to take care of also increases. Every data block in the storage pool would consume some amount of name node's main memory. So it is important for the name node to have enough main memory so that it can properly manage the pool of data blocks. As a rule of thumb, 1000 MB per million storage blocks is recommended. Let us take an example of a 100 node cluster with 4 TB disks and let the block size be 64 MB. Then the number of storage blocks would come out to be 2 million. That means name node should have around 2 GB of main memory. In the next slide are the few key points from the last two lessons. Please pause the video if you may like more time to read.